This video is on gas laws. Question 1. Define and give the units for each variable for pressure, P equals F over A. Pressure is defined as force per unit area. It's a scalar. It's the total force acting on an object divided by its total surface area from that force. Has units of newtons over meters squared or Pascal. Question 2. The surface area of an average human male foot is approximately 651 centimeters squared. Determine the pressure on each foot of a 75 kilogram man standing on both feet. So the total force is the force of gravity, and the area is the area in meters squared. And you have to multiply it by 2 since there's 2 feet. Question 3. Define Avogadro's constant N sub A. It's the number of particles in a mole. And it's about 6.02 times 10 to the 23 particles per mole. Question 4. Define and give the units for each variable for a mole. Little n equals big N over N sub A. So little n is number of moles, big N is number of particles, and N sub A is Avogadro's constant, which we were just talking about in number 3. So an example, instead of saying 12 eggs, you could just say 1 dozen eggs. If you have 6.02 times 10 to the 23 eggs, you could just say 1 mole of eggs. Question 5. Determine the number of moles of determine the number of molecules in 3.25 moles of O2. So they gave you little n, and we know what N sub A is. It's a constant. So we could just solve for big N. Number 6, determine the number of moles of 1.47 times 10 to the 26 particles. They gave us big N, and we know N sub A. It's a constant, so we could solve for little n. Question 7. Consider H2O. What is the molar mass of H2O? So you need to look this up in the periodic table of elements. It's 18 grams. How many moles are in 50 grams of H2O? We're going to convert grams to moles. 1 mole has 18 grams for H2O. Part C, how many grams are in 18 moles of H2O? We start with 18 moles, and we want to end up getting grams. So we need moles on the bottom and grams on the top. So the left hand cancels, and we end up getting grams. Number 8, consider CO2. What is the molar mass of CO2? So you need to look this information up in the periodic table of elements. If you don't really understand how I got 44 grams, then just ask your chemistry teacher. Because carbon is 12 grams, oxygen is 16 grams. How many moles are in 26 grams of CO2? So we want moles in the end. And we were given 26 grams in the problem. And we know 1 mole is 44 grams. So the mole needs to be in the numerator, grams needs to be in the denominator. Part C, how many grams are in 32 moles of CO2? So we want grams on the right hand side, because that's what the problem is telling us. And we're going to start with 32 moles. So if we have 32 moles, we need something with moles in the denominator, grams in the numerator. So units cancel. One more example. Consider CH4. What is a molar mass of CH4? Once again, ask your chemistry teacher if you don't quite understand how I got this. Carbon has a mass of 12 grams, hydrogen 1 gram, and there's 4 hydrogens. Part B, how many moles are in 46 grams of CH4? So we want moles as the solution, so we write moles on the right hand side. And we're given 46 grams, which we start with. So if we want to convert grams to moles, we need something with grams on the denominator, moles in the numerator. Part C, how many grams are in 146 moles of CH4? So we're going to want grams at the end. We're going to start with 146 moles. And if you want to convert moles to grams, on the left-hand side, if we're starting with moles, we need moles in the denominator, grams in the numerator. Question 10. Define and give the units of atomic mass unit U. Atomic mass unit U is defined as a neutral carbon-12 atom having exactly 12 atomic mass units. This means that one atomic mass unit is defined as having the mass of 1/12 the mass of a neutral carbon-12 atom. Question 11. State some characteristics of an ideal gas. So memorize this, because many times in multiple choice and free response questions they want you to write some characteristics of an ideal gas. High temperature, low density, and low pressure. Because low temperature, high density, high pressure ends up giving you a liquid or a solid. All collisions between particles are perfectly elastic. That means kinetic energy initial equals kinetic energy final, and momentum initial equals momentum final. Momentum initial equals momentum final is always true, because that's the law of conservation of momentum. No intermolecular attractive forces, meaning like no force of gravity. All the internal energy is in the form of kinetic energy, meaning no potential energy. All particles are taken as points with no volume. Duration of a collision is negligible compared to the time between collisions. Finally, molecules move randomly and have a range of speeds. Question 12. What are some differences between an ideal gas and a real gas? An ideal gas cannot exist at low temperatures because it will convert to a fluid. Under high pressures and low temperatures, all gases can be liquefied and can be almost incompressible. There are short-range repulsive forces between gases when they approach each other. There are attractive forces between gases when they are away from each other. Van der Waals equation is a modification of the ideal gas law. So we'll learn more about the ideal gas law in a moment, hopefully. Question 13, define and draw a graph showing Boyle's law. So if the temperature and number of molecules of an ideal gas in a closed object are constant, then pressure is inversely proportional to volume. Okay. So if the volume of an ideal gas in a closed object increases, then the pressure will decrease, and vice versa. We could also look at it as this. We could take the inverse of both sides. If the pressure of an ideal gas in a closed object increases, then the volume will decrease. So we could also look at this equation here. P1V1 equals P2V2. If you double the volume, then the pressure decreases by half. And if you decrease the volume by half, then the pressure doubles. So you have these two graphs. This is pressure versus volume on the left side. This is pressure versus 1 over volume on the right side. Question 14, define and draw a graph showing Charles's law. So if the pressure and number of molecules of an ideal gas in a closed object are constant, then the volume of the closed object divided by the temperature of the ideal gas is a constant. So V over T equals a constant. So if the volume increases, then the temperature increases. If the volume decreases, then the temperature also decreases. So if you double the volume, then the temperature doubles. And if you have the volume, the temperature will have. So this is what a volume versus temperature looks like. The reason why there are dotted lines here is because if the temperature of an ideal gas is too low, then it becomes an incompressible liquid or solid. So the temperature cannot be this low. The temperature for an ideal gas has to start above absolute zero. Question 15. Define and draw a graph showing Gay-Lussac's law. If the volume and number of molecules of an ideal gas in a closed object are constant, then the pressure of the ideal gas in the closed object divided by the temperature of the ideal gas is a constant. So P, pressure over temperature, is equal to constant. So we have this graph here. So make sure temperature is in Kelvin. And once again, the reason why we have a dotted line here is because the temperature cannot start at absolute zero. It has to be a bit above it. Because if the temperature is too low, the gas becomes a liquid. Question 16. Take Boyle's law, Charles' law, and Gay-Lussac's law to obtain a general equation for an ideal gas. So PV over T equals a constant. Question 17. Define and give the units of each variable for the ideal gas law. So this is the ideal gas law. Pressure times volume equals number of moles times a constant, it's called the gas constant, times temperature. Question 18. We have another ideal gas law, PV equals N K sub BT. So look at 17 and 18. 17 has a little n. 18 has a big N. Little n is number of moles, big N is number of particles. Question 17 has big R. Question 18 has K sub B. Big R is a constant, K sub B is a constant. So make sure you know the difference between these two laws. They're both ideal gas laws. Question 19. What is the number of what is the number of moles of an ideal gas in 80 centimeters cube at room temperature of 20 degrees Celsius and a pressure of 1 times 10 to the 5 pascals? So start with PV equals nRT. Solve for little n. We get a solution. Question 20. What is the volume of 22 moles of an ideal gas when it fills a cylinder at a temperature of 40 degrees Celsius and a pressure of 1.01 times 10 to the 5 pascals? This is our volume. See that degrees Celsius was converted to Kelvin. Question 21. Finally, we're solving for the temperature. And we get this, which is pretty darn cold. So now we're going to use this equation. P1 V1 over P2 equals nRT1 over nRT2. Question 22. 3 moles of an ideal gas originally occupies a volume of 120 centimeters cubed with a pressure of 1.01 times 10 to the 5 pascals at a temperature of 23 degrees Celsius. So this first sentence gives us everything we need to know for the numerator. What will be its new volume if its pressure is held constant? So P1 is equal to P2 and its temperature increases. So P1 equals P2, number of moles didn't change, so N1 equals N2, and the gas constant is just a constant. So things cancel in this first equation here, where we just end up getting V1 over V2 equals T1 over T2. So we end up getting this equation, 126 centimeters cubed. Question 23. 5 moles of an ideal gas originally occupies a volume of 160 centimeters cubed with a pressure of 1.01 times 10 to the 5 pascals and a temperature of 23 degrees Celsius. This first equation tells us everything for the numerator, P1, V1, T1. What will be its new pressure if its volume is held constant and its temperature increases to 75 degrees Celsius? It just says volume is constant, so V1 equals V2, N1 equals N2. We know little n stays the same. So things cancel, so we just get P1 over P2 equals T1 over T2. We're solving for P2. Where we get this. Question 24. One more example, I believe. 2 moles of an ideal gas originally occupies a volume of 346 centimeters cubed with a pressure of 1.01 times 10 to the 5 pascals at a temperature of 30 degrees Celsius. So this first sentence tells us everything about the numerator. What will be its new pressure if its volume increases to 362 centimeters cubed and its temperature is held constant? It just says its temperature is held constant. So T1 equals T2, N1 equals N2. Things cancel where we get this, which is highlighted. Solving for P2, we get this. Sorry, one more. A sphere with a volume V contains 30 milligrams of an ideal gas with a pressure P. An additional mass of the gas is added to the sphere while the temperature is kept constant. So the additional mass is going to be 30 milligrams plus X. The pressure of the sphere increases to 4P, while the volume of the sphere increases to 3V. Calculate the amount of gas added to the sphere. So PV equals nRT. N is mass divided by molar mass, which is little m divided by big M. So PV equals little m over big M times RT. Pressure increases to 4P, volume increases to 3V. Little m increases to 30 plus X. Big M stays the same, times RT. So this first highlighted equation is the initial condition. The second highlighted equation is the new condition. So divide the two highlighted equations above, and we get this. And now we could solve for X. Question 26. Define and give the units for each variable for the equation for the kinetic theory of an ideal gas. P equals 1/3 rho v squared. This equation tells us that the change in momentum of particles due to collisions with a given surface gives rise to pressure in gases. And from that analysis, pressure is related to the average translational speed of gas molecules. So P is pressure, rho is density, V is average speed of an ideal gas. Question 27. The density of air on Earth is approximately 1.29 kilograms per meters cubed at a pressure of 1.01 times 10 to the 5 pascals. Assume the Earth is an ideal gas. Determine the average speed of the air. So the average speed of air is about 500 meters per second. Crazy, yeah? Question 28. The density of air on Mars is approximately 0.2 kilograms per meters cubed at a pressure of 610 pascals. Assume the air is an ideal gas. Determine the average speed of the air. We start with this equation. We solve for V. It's about 100 meters per second. Question 29. Define and give the units for each variable for the equation for the internal energy of an ideal monatomic gas. This equation gives a relationship between the internal energy U of an ideal monatomic gas and the number of molecules or amount of substance. So here I'm just going over what each variable means. So the important thing to learn from this question is U equals internal energy of an ideal gas. Question 30. Determine the internal energy of 7.42 moles of an ideal gas at a temperature of 32 degrees Celsius. So let's convert Celsius to Kelvin, degrees Celsius to Kelvin. And we know energy has the units of joules. 31, same problem. Solving for internal energy. Question 32. Use the equation average kinetic energy equals 3/2 K sub BT to determine the average kinetic energy and speed of O2 at a room temperature of 20 degrees Celsius. So the average kinetic energy, we're going to have to find the average kinetic energy and speed of O2. So step 1, convert degrees Celsius to Kelvin. Step 2, determine the average kinetic energy, which is what they wanted us to do. Step 3, we have to find the mass of O2 in kilograms. Step 4, use this equation, 1/2 mv squared, to find the average kinetic energy. It's about 478 meters per second. Now this is good because our solution for 32 is similar to our solution for 27, which is the average speed of air. So these two numbers are very similar to each other. Question 33. We're going to use the equation 3/2 K sub BT to determine the average kinetic energy and speed of CO2 at a temperature of 23 degrees, assuming CO2 is an ideal gas. So step 1, convert temperature to Kelvin. Step 2, let's use this equation to find the average kinetic energy, which is this. Step 3, determine the mass of CO2 in kilograms. We have 2 unit conversions. We get this. And finally, we're going to use 1/2 mv squared to solve for average speed. It's 409 meters per second. So CO2 is heavier than O2. So that's why it's a bit slower. Average speed of CO2 is 409 meters per second. Average speed of O2 is 478 meters per second.